Hello and welcome to the first of several tutorials on subsets. Today we will learn about what are called pairs. In video number 9 we will learn about what are called triplets, and then the larger subsets of 4, 5, and 6 will be covered in my advanced series. But today we will focus on pairs. In normal life we think of a pair as being just two of the same thing. Like in poker, you might have a pair of queens, which would mean you have two queens. Or you might think of a pair of socks, meaning you have exactly two matching socks. But in Sudoku, the term pair has a slightly different meaning. It's more like having two pairs. Let me show you what I mean. If you remember from the terminology video, a subset in Sudoku is defined as n number of candidates in n number of cells. Like 2 candidates in 2 cells, or 3 candidates in 3 cells, or 4 candidates in 4 cells, etc. And further, the cells and the candidates of the subset must be contained entirely within at least one house, i.e. a row, a column, or a 3x3 block. And don't forget, there is no such thing as a subset of 1. If you have one candidate in one cell, and it is the only occurrence of that candidate in a particular house, even if it is hidden, it will be the solution to that cell, and so you need not go any further except to solve that cell for that digit, okay? So the smallest subset is of 2 candidates, and these are called pairs. Now, something like this does not constitute a pair in Sudoku. Even though it kind of looks like what might be considered a pair because it is 2 numbers or 2 candidates, this all by itself is called a by-value cell. Don't forget that, a by-value cell. And these will come into play over and over again in a multitude of the solving techniques we will be learning. A by-value cell is one in which there are only 2 remaining candidates, 2 possibilities. Now, there is a conventional strong link between the 2 candidates in a by-value cell. And this further means that one of them must be true and the other must be false. When the puzzle is solved, this cell in row 1, column 5, must be filled with a value. And since there are only 2 possibilities, one of them must be true and the other must be false. Okay, now let's get back to pairs. In Sudoku, a subset of a pair is defined as 2 candidates in 2 cells that both lie in the same house. Remember that. 2 candidates in 2 cells that both lie in the same house. And these come in 3 varieties: naked, hidden, and locked. A naked pair is one in which the 2 candidates are the only candidates in the 2 cells. A hidden pair is when the 2 candidates are contained in only 2 cells of a particular house, but they are camouflaged by the presence of other candidates. And a locked pair is simply a naked pair or a hidden pair that lies in 2 houses at the same time. Now first, let's take a look at some naked pairs so we can understand their implications. A naked pair is simply 2 identical by-value cells that both lie within at least one house. Here are some examples. Okay, here we have 3 sets of naked pairs. One in row 1, one in column 2, and one in block 9. Now, as I said in the opening, these pairs, these subsets of a pair, look more like 2 pair than they do 1 pair. Now, a friend of mine gets mad at me when I say pair because he thinks it should be pairs with an S on the end. Actually, it's correct either way. You can say 2 pair or 2 pairs. So we'll use the S and we'll say 2 pairs. So the 7 and the 6 and the 7 and the 6 in row 1 look like 2 pairs of 7 and 6. And that's what it is. But that's called a subset of a pair. Now let's think about what this means. Imagine that there are other candidates in the other 7 cells in row 1. But I just want you to focus on the two cells that contain the 7 and the 6, and the 7 and the 6. Now, when the puzzle is solved, one of those cells must be a 7 and the other must be a 6. That's the only way it can be. Now, we don't know which. We don't know if the first one is the 7 or the first one is the 6. But regardless, whichever one is the 7, the other one is the 6. And whichever one is the 6, the other one is the 7. And as you can see, if we solve this first cell here for 7, it leaves a naked single in the other cell. And so that has to be 6. And likewise, if we solve the first cell for 6, it leaves a naked single of a 7 in the other cell. So one of those cells has to be a 6 and the other one has to be a 7, but we don't know which. But what this means is all the other 7 cells in row 1, they cannot contain a 7 or a 6 because the 7 and the 6 must go into those two cells, into row 1, column 5, and into row 1, column 8. Those have to be the 7 and the 6. So those are spoken for, which means if there is a candidate 7 or a candidate 6 anywhere else outside those two cells in row 1, they have to be false and you can eliminate them. Okay? Now let's take a look at column 2. The same thing. We have a 2 and a 5 and a 2 and a 5. So if one of those is a 2, the other one is a 5. Okay? And if the first one is a 5, then the other one is a 2. And that's the only thing it can be. Because column 2 has to contain a 5 and a 2, and because those two by-value cells only contain those candidates, one of them must be the 2 and the other one must be the 5. Now we don't need to know which one is which, but we know that all the other cells in that column cannot be 2 or 5, which means you could eliminate any candidate 2 or any candidate 5 that lies in column 2 outside those two colored cells. And then likewise in block 9 must contain a 3 and it must contain a 9, and because those two by-value cells are in there with only 3 and 9, one of them has to be the 3 and the other one has to be the 9. Or the first one could be the 9 and the other one could be the 3. But that's the only way it can be. So all these other cells, 1, 2, 3, 4, 5, 6, 7, there cannot be a 3 or a 9 in any one of those other 7 cells in block 9. Does everyone understand that? Now notice that this does not constitute a subset of a pair because the two cells do not lie in the same house. Understood? Okay, good. The pairs must lie in the same house. Like the 7 and the 6 and the 7 and the 6, they both lie in row 1. The 2 and the 5 and the 2 and the 5, they both lie in column 2. And the 3 and the 9 and the 3 and the 9, they both lie in block 9. That's why you can make those eliminations. Any cell that's outside those houses cannot be affected by the presence of those naked pairs. Okay? Now with the naked pair, the eliminations are made outside the two cells containing the naked pair, but in the same house. And the eliminations, if any, are of the other instances of the same digits as the pair itself. Like for instance, let's take a look at the 7 and the 6 and the 7 and the 6 in row 1. We know that row 1, column 5 must be a 7 or a 6, and row 1, column 8 must be a 7 or a 6. Therefore, there cannot be a 7 or a 6 in any other cell in row 1. So you can eliminate this 7 and this 6, and you can eliminate this 6 and this 7, and you can eliminate that 6, and you can eliminate that 7 and that 6, and you can eliminate that 6. Now, I didn't count them, but that's a lot of eliminations based on the presence of that naked pair. Now next, we're going to take a look at the 2 and the 5 in column 2. And you can eliminate any candidate 2 or candidate 5 that lies in column 2 outside the two colored cells. So you can eliminate that 2 and that 5. You can eliminate that 5 and that 2 and that 5. You can eliminate that 2 and that 5. You can eliminate that 5 and you can eliminate that 2 and that 5. Because The two colored squares must contain the 2 and the 5. So no other cell in that column can contain a 2 or a 5. They must all be false. And likewise, let's take a look at block 9. There can be no other 3 or no other 9 in the whole block. So you can eliminate that 3 and that 9. You can eliminate that 3. You could eliminate that 3 and that 9. You can eliminate that 3 and that 9, that 9, and that 9. Because one of those two bi-value cells with the 3 and the 9, one of them has to be the 9 and the other has to be the 3. Okay, now let's take a look at some hidden pairs and see how they work. Now, hidden pairs work just the opposite of naked pairs. The naked pairs are blatantly obvious because you see two cells in the same house that have only two candidates each, the same two candidates. But a hidden pair is camouflaged by the presence of other candidates, and they're so much harder to see, and you have to be able to ferret out their existence in the midst of all those other candidates. So for instance, let's take a look at row 1 here. If you look very carefully, you will see that there is no other 7 and no other 6 in any cell except the two dark colored cells. So what this means is one of them has to be the 7 and one of them has to be the 6. But the difference here is the eliminations are made within the cells containing the pair. So you can eliminate all the other candidates besides the 7 and the 6 in those two colored squares. So that means you can eliminate this 1, the 5, the 3, and the 9, and you can eliminate the 4, the 2, the 5, and the 8. Because that pair of 7 and 6 was in there all along, but it was covered up and disguised by the presence of those other candidates. Now, if a 7 or a 6 were to occur in any one of those other cells in that row, then that wouldn't be a hidden pair. For instance, let's go back. Now, if there was a 7 here and a 6 here, then that's not a hidden pair in those two cells, because one of these cells could be the 7 or the 6. And we don't know for sure that row 1, column 5, and row 1, column 8 has to be the 7 and the 6. But if this 7 and this 6 are not there, then even though there are other candidates in those two colored cells, those two cells still have to be the 7 and the 6 because they don't appear anywhere else, which means you can make those eliminations within those cells. You see? Okay, now let's go to the 2 and the 5 in column 2, and we see that there is no other 2 and no other 5 in column 2 except for in row 4, column 2, and in row 7, column 2. And so we know that one of those two cells has to be the 2 and the other one has to be the 5, and therefore all the other candidates in those two cells are false. And you can eliminate them like that. And lastly, in block 9, we look carefully and we see that only these two darker colored squares have the 3 and the 9. And the 3 and the 9 do not appear anywhere else in that block, which means those two cells, row 7, column 9, and row 8, column 8, they have to contain the 3 and the 9, which means you can eliminate every other candidate in those cells except for the 3 and the 9. Like that. Now with a naked pair, the eliminations are made outside the two cells containing the naked pair, but in the same house. And the eliminations, if any, are of the other instances of the same digits as the pair itself. And with a hidden pair, the eliminations are made within the two cells containing the hidden pair, and thus the eliminations are of digits other than the pair digits. So naked and hidden pairs appear quite differently when you are looking for them. So now let's take a look at the last variety of pairs called locked pairs. A locked pair is exactly the same as a naked pair, except that it lies in two houses at the same time. It will be two identical by-value cells that lie in the intersection of either a row and a block or a column and a block. And because it lies in two houses simultaneously, the effects apply to both houses. And just like a naked pair, the eliminations occur outside of the two cells. So let's see what this looks like. The intersection of a row and a block looks like this. The three yellow cells are the intersection cells. They lie in both houses at the same time. They lie in row 1 and in block 2. And the intersection of a column and a block looks like this. Again, the three yellow cells are the intersection cells. Those three yellow cells lie in column 6 and in block 5 at the same time. And the intersection of a row and a column looks like this and is only one cell. So this will not come into play when we're talking about subsets because subsets require two or more cells. So in order for a pair to be locked, it has to lie in the intersection of a row and a block like this, or in the intersection of a column and a block like this. So here we have a naked pair of 7 and 6 and 7 and 6, and as before, it lies in row 1. So because we know one of those has to be a 7 and the other has to be a 6, there can be no other candidate 7 or no other candidate 6 in any of these cells in row 1. The red cells are the elimination cells. But now, this time, this naked pair, not only does it lie in row 1, it also lies in block 2. So that means the same thing applies to block 2. So 7 and 6 have to be the solutions to those two yellow cells, which means candidate 7 and candidate 6 cannot exist in these other 6 cells. So there's a total of 13 cells where you can make eliminations because of this locked pair. And here again we have another naked pair of 7 and 6 and 7 and 6, and this time they lie in row 4. So we know that none of these cells can contain a 7 or a 6 because those two yellow cells must be solved with 7 and 6. But those two yellow cells also lie within block 6. So that means these other 6 cells cannot be a 7 or a 6 either. So any 7 or any 6 in any one of those red cells can be eliminated as false. Now let's take a look at a column. And as before, we have a naked pair of 2 and 5 and 2 and 5 that lie in column 2. But this time they also lie within block 4. So that means you can eliminate any candidate 2 or any candidate 5 from all 13 of these cells. Like again, there may not be any there, but if there are, they have to be false because those two yellow cells must be solved with a 2 and with a 5. And again, we have a 2 and a 5 over here in column 8, and they lie in block 3 as well. So that means there can be no other candidate 2 or no other candidate 5 in any one of those red cells. I hope that's clear. So now let's take a look at some examples in some real puzzles of all 3 types of pairs: naked, hidden, and locked. Naked pairs are fairly easy to find, they're fairly easy to see, and they are pretty easy to understand as well. So we should be able to go through these examples rather quickly. Okay, here in this first example, in block 7, we see we have a naked pair of a 7 and a 3 and a 7 and a 3. And because they lie in block 7, there can be no other 7 or no other 3 in block 7 because one of the 2 yellow cells must contain a 7 and the other must contain a 3. It doesn't matter which, we can still eliminate all 7s and all 3s from the rest of the block. So we can eliminate that 3, that 3, that 3, and that 7. Okay? Next puzzle, we have a naked pair of a 5 and a 9 and a 5 and a 9 in column 3. So there can be no other 5s or no other 9s in column 3. So we can eliminate that 5 and that 9. We can eliminate that 5, that 9, and we can eliminate that 5, which leaves a naked single there, but we're not worried about that right now. All right, so the next puzzle, we have in row 4, we have a naked pair of 4 and 5 and 4 and 5. So we can eliminate all the 4s and 5s that lie outside those yellow cells in row 4. So that 4 is false, that 4 is false, and that 4 is false, and that 5 is false. All right, next. Here in block 6, we have a naked pair of 1 and 3 and 1 and 3. So we can eliminate that 1, that 3, that 3, that 1, and that 3, and that 3. Got it? Next one. In column 5, we have a naked pair of 5 and 8. So 5 and 8 cannot occur anywhere outside those yellow cells in column 5. So you can eliminate that 5, and you can eliminate that 8, and you can eliminate that 5 and that 8. Next puzzle. Okay, here in row 7, we have a naked pair of a 2 and a 5 and a 2 and a 5. So we know that one of those yellow cells must be a 2 and one must be a 5. So we look down the row and we see that we can eliminate this 2 and this 5, this 2 and this 5, and that 2. You know, sometimes there is only one elimination to be made and sometimes there are none. So you just have to make as many as you can and move on. The next puzzle here, we have a naked pair of 4 and 5 and a 4 and a 5 that lie in block 5. So we can eliminate every 4 and every 5 in block 5 outside of the yellow square. So that 4 is false, that 5 is false, that 4 is false, that 4 or that 5 are false, and that 4 is false. Next one, in column 7, we have a naked pair of 7 and 8. So we can eliminate that 7 and that 8 and that 8 and that 7. The next puzzle, in row 8, we have a naked pair of 4 and 6. So we can eliminate all the 4s and 6s out of that row outside of the yellow cells. So we can eliminate that 6, that 4, that 6, that 4, and that 6. And then lastly, in column 2, we have a naked pair of 7 and 5 and 7 and 5. So one of those must be the 7 and one must be the 5. Therefore, all other 7s and all other 5s in column 2 are false. So it's that one, that 5, that 5, that 5, and that 7. And there you have it. That's naked pairs. So next we have hidden pairs, which are much more difficult to find. So we should spend a little more time on those. Now, in order to find hidden pairs, you have to have a discerning eye, a keen eye, because they're not going to jump out at you. You've got to go searching for them. You've got to dig them out, and they are hard to see. But just like anything else, the more you do it, the better you'll get at them. And who knows, maybe they'll become your specialty. Anyway, here in this puzzle, we take a look at row 5, and we see that there are only 2 7s and 2 8s in all of row 5, and they both lie in the same cells, so that is a hidden pair, here and here. And because there are no 7s or no 8s anywhere else in row 5, we know that all the other candidates in those cells must be false. So you can eliminate the 4, the 6, and the 3, the 4, the 6, the 3, and the 2. Now also this leaves what looks like also a locked pair, but there are no other 7s or 8s in block 5, so there are no further eliminations to be had. But if you have a hidden pair and once you reveal them, that you see that it lies in another house, then you can make the eliminations in that house as well. But in this case, there aren't any. Okay, next puzzle. If we look down here in block 8, we see that there are only 2 candidate 4s and only 2 candidate 2s, and they both lie in the same cells, and they do not appear anywhere else outside of those cells. They are here and here. So that is a hidden pair, which means you can eliminate all the other candidates out of those cells except for the 4 and the 2, like that. Okay, next puzzle. If we take a look here in row 6, we see that there are 2 candidate 7s and 2 candidate 6s, and they both lie in the same cells, and they do not appear anywhere else in that row outside those cells. So that is a hidden pair right there, 7 and 6 and 7 and 6. So you can eliminate the 2 and the 3, and you can eliminate the 2, the 3, and the 5. Again, that leaves a locked pair, but there are no other 7s or 6s in block 5, so nothing further can be done in this case. Now, what you will begin to notice is sometimes 2 or 3 different solving techniques will produce the same result, but by different means. And it doesn't matter which one of those techniques you use, as long as you find just one of them to solve a particular cell or make the legal eliminations. And along these lines, hidden pairs are many times discovered or revealed by eliminating the extra candidates in the 2 cells as a result of one or more different solving techniques, as well as simply spotting them as a hidden pair. Okay, let's go on to the next puzzle. In column 7, we see that there are 2 candidate 1s and 2 candidate 9s, and they both lie in the same cells. So there is a hidden pair, 1 and 9 and 1 and 9. There are no other 1s and no other 9s in column 7 except in those 2 cells. So that means the 5 and the 8 are false, and that means the 5 and the 7 here are false, because one of those 2 cells must contain the 1 and the other one must contain the 9, because those candidates do not appear anywhere else outside those cells. Okay, next puzzle. Again, in column 7, we see that there are only 2 candidate 4s and only 2 candidate 2s, and they lie here and here. The 4 and the 2 do not appear anywhere else in column 7 outside those 2 cells. Therefore, they must be the solutions to those 2 cells, and you can eliminate the 7, the 6, and the 3, and you can eliminate the 1, the 7, and the 8. Now let me show you a little trick. Let's go back, put those candidates back in there, and let's uncolor these cells. Now when you're using filters and cycling through the candidates, if you happen to notice that there are just 2 instances of a certain candidate, put that in the back of your mind, and then when you're looking for a different candidate, you see those same 2 cells are lit up, then you know that's a hidden pair. For instance, if you turn on the filters for 4, and you see in column 7 there are only 2 instances of candidate 4. Now let's look at the filter for candidate 2, and we see those same 2 cells are lit up. So that identifies your hidden pair. And sometimes you can use that as a test to make sure you're not seeing double or anything like that. You just test the filters, and if it lights up the same 2 cells, you know you've found a hidden pair. All right, let's go to the next one. Let's take a look at block 8, and we see that there are only 2 candidate 5s and 2 candidate 6s, and they lie in the same 2 cells. They are here and here. 5 and 6 do not occur anywhere else in block 8 except for those 2 cells, so that is a hidden pair, and we can eliminate all the other candidates in those 2 cells except for the 5 and the 6, because one of those cells must be a 5 and the other must be a 6. All right, let's go to the next one. Let's take a look in row 5, and we see that there are only 2 candidate 1s and only 2 candidate 2s, and they lie in the same 2 cells. So that is a hidden pair. Because they don't occur anywhere else in that row or the block, we can eliminate the other candidates from those 2 cells. We can eliminate the 3, the 4, and the 7, and we can eliminate the 4 and the 9. And like I said, if you find a hidden pair with respect to a row and find that it's also a locked pair inside a block too, you can make the eliminations inside the block after the hidden pair is revealed. But in this case, again, there are no other 1s and 2s in block 6. All right, next puzzle. Okay, in column 2, we see there are 2 candidate 1s and 2 candidate 6s, and they lie in the same 2 cells. They are here and here. So those are the only two 1s in column 2, and those are the only two 6s in column 2. So that is a hidden pair, which allows us to eliminate all the other candidates except for the 1 and the 6. One of those cells has to be a 1, and the other has to be a 6 because they do not lie anywhere else outside those two cells in column 2, or block 1 as well. Okay, the next one. In column 5, we see that there are two candidate 3s and two candidate 6s that lie in the same two cells. They're here and here. So the solutions to those two cells must be the 6 and the 3 because they don't lie anywhere else in that column or the block. So we can eliminate the other candidates from those two cells, which are the 1, 2, 4, and 5, and the 1, 2, and the 5, leaving the naked pair. Next, we look in column 3 and we see that there are only two candidate 2s and two candidate 6s, and they lie here and here. Candidate 2 and candidate 6 do not lie anywhere else outside those two cells in either column 3 or block 7. So you can eliminate all the other candidates out of those two cells, leaving the 2 and the 6. And lastly, let's take a look in block 1, and we see that there are only two candidate 7s and two candidate 9s in block 1. So there is a hidden pair. They do not occur anywhere else in that block except for those two cells. So they must be the solutions to those two cells. One must be a 7 and one must be a 9. So we can eliminate the 4 and the 2, and we can eliminate the 8, the 5, and the 2. So there you have it. Those are hidden pairs. And like I said, they're very hard to find, but the more you practice, the better you will get at finding them. So now let's take a look at the last type, which are locked pairs, which are very similar to naked pairs, except they apply to two houses. And unlike these hidden pairs, they are very easy to find. Okay, this video is getting kind of long, and these are pretty straightforward, so we should be able to burn right through them. These are locked pairs, and what they are naked pairs, but they lie in two houses at the same time. They will lie in the intersection of a row in a block or in the intersection of a column in a block. And you can make all the eliminations in both houses. So here we have a 4 and an 8 and a 4 and an 8. That is a naked pair, but it lies in row 8 and block 9. So you can eliminate every 4 and every 8 out of both the row and the block. So there's a 4 here and a 4 here in the row. Now in the block, 4, 8, 4, 8, 4, 4. Because one of those two yellow cells must be a 4 and the other must be an 8. So those candidates cannot appear anywhere else in both the row and the block. Okay, next. Here we have in row 7 and in block 8, we have a naked pair of 3 and 9, which is a locked pair. So you can eliminate candidates 3 and 9 from row 7 outside those cells, and in block 8 outside those cells. All right, next we have a naked pair that lies in a column and a block. Column 1 and block 4, we have 7 and 9, and 7 and 9. So those two candidates cannot appear anywhere else in the column or the block. All right, these are pretty simple, right? Okay, next one. We have a 4 and a 7, 4 and a 7. That is a naked pair, and it is locked because it is in column 7 and block 9. So you can eliminate this 7 and that 4 and that 4 and that 7, and now in the block, 4, 7, 7, 4, 7, 4, 7, 7. Now that's a lot of eliminations, and these are very powerful because they're affecting two houses simultaneously. All right, the next one we have a naked pair of 4 and 9, 4 and 9 that lies in row 3 and block 1. So you can eliminate the 4 and the 9 from the block and from the row. I hope I don't miss one. All right, there we go. Next puzzle we have in row 8 And in block 8, we have 1 and 9, so you can eliminate the 1s and the 9s from row 8. There's 1 there, 1 there, 1 there. And the 1s and the 9s from block 8. 1, 9, and 1, 9. Okay? Next one, we have a 4 and a 3, a 4 and a 3 in row 7 and block 7. So going down the row, there's only 1, 3, and 1, 4. And the block, there's a 4, and a 3, and a 4, and a 3. Okay, the next one, we have a 3 and a 9, 3 and a 9. They lie in column 4. I'm starting to get confused here. They lie in column 4 and in block 2. So you can eliminate the 3 and the 9 from the rest of the block, and you can eliminate the 3 and the 9 from the rest of the column. All right, the next one, we have 4, 2, 4, 2, a naked pair. One of them has to be a 4, the other one has to be a 2. So you can eliminate the 4 and the 2 from the rest of the row, row 2, and you can eliminate the 4 and the 2 from the rest of the block, from block 1. That is a locked pair. Here's another one. We have 2, 9, 2, 9 in row 7 and block 8. So you can eliminate this 2 and this 9, that 9, and that 2. And then in the block, you can eliminate that 2 and that 9. And lastly, we have a 2 and a 5 and a 2 and a 5, a naked pair. One must be a 2 and one must be a 5 because they lie in 2 houses at the same time, so they rule both houses. So you can eliminate the 2 and the 5 from the column, and you can eliminate the 2 and the 5 from the block. So there you have it. That's it for today. Those are the 3 different types of pairs, and I hope you understand how they work now. So let's go back outside and finish up. Pairs in all 3 varieties are one of the most commonly occurring patterns or solving techniques you will encounter when solving puzzles of any difficulty level. And they will occur at any stage of solving the puzzle from the very beginning to the very end. Naked and locked pairs are easy to find. Finding the hidden ones takes some practice, but over time I'm sure you will begin to find them too with little or no problem whatsoever. Well, there you have it. Pairs are pretty easy to understand, and we've covered enough examples in today's lesson that I don't think there's any need for an adjunct video. So I will see you in video number 9, where we will take what we learned today and kick it up a notch to subsets of 3, which are known as triplets or triples. Until then, be well and be happy.